Hello class. So in today's video, we will walk through a use case of insurance companies and how they can utilize the location data to make their policies related to premiums. So while there are many use cases of insurance such as fraud detection, risk assessment, and many others, the use case that we will be analyzing in today's class is the earthquake risk assessment. That is, we will be analyzing how likely an area in the United States is likely to have an earthquake based on the seismic activity that's happening in that place, and based on the historical earthquake data. So the data that we will be using in today's class is the seismic data and the historical earthquake data. So using these two data, we'll be analyzing which areas are more likely to have an earthquake and how the information derived from this analysis can be utilized by the insurance companies to determine the amount of premiums to be charged to the residents of those areas. At the end of the video, we'll be creating a visualization that will be similar to this one. So just to give you a quick preview of the graph or the visualization that we will be deriving is that so this is the map of United States, and this area over here, they represent the seismic activity. And the pink bubble-like structures, or the circular structures over here, they show, they represent the historical data point of the earthquake incidents that happened in those areas. Bigger the size of the circle, the more magnitude earthquake happened, the earthquake of more magnitude happened in that area. So using, so combining the seismic data record and the earthquake data, we will sort of try to help insurance companies to analyze the risk associated with certain areas in the United States and to derive policies on how much premium should they be charging to the residents of those areas. So without further ado, let's get started. I am going to start my QGIS over here. I'm going to minimize this. And okay, it's getting started. So I have my QGIS opened over here. So the first thing that we will be doing is we will import a shapefile based on a data from the US Geological Survey that details the risk of experiencing a damaging earthquake in all of the states of United States. So that file is located over here. Okay. So this is the shapefile that I need to import. So, okay. The first thing I'll do is this, and then I will just drag and drop. Okay, now that I have it over here, the next thing that I'm going to do is import a base map for this project. So in this case, we will use two Earth shape files to do this. You can also use the OpenStreetMap that can be found over here in the QGIS itself. But for this case, like I'll be using the other two natural Earth shape files that I already have in the folder. But that's totally up to you. It's optional. But because I already have the shape file, the natural Earth shape file, so I'll just use it for now. So I have it, those files, I have it over here. So I will just import that shape file, which I'm going to drag and drop down underneath the seismic risk clip. And then the next file is I will import the lakes shape file. This again is optional. I mean, this is sort of, this shapefile, the lakes shapefile, is a shapefile that denotes, all the lakes, major lakes, I would say, indicates indicates the location of all the major lakes or the major water bodies in the North American continent. So importing those two files is optional, but because I already had it, I'm just using it because I have it. Okay, So that this is optional. And regarding this one, this is something, this shapefile is something that you may like to use it in other projects as well, depending on your preference, whether to use the OpenStreetMap or, the shapefile or the Natural Earth shapefile that I got from the Natural Earth website. So that site has the, shapefile of the major Earth locations of, let's say, like all the continents. So yeah, so this is again optional, but because I already had the shapefile for this one, I'm just using it just to let you know that, there are shapefiles available for all the 7 continents of the world. And yeah, so this is optional. Next, we will go to the seismic risk layer. So we will open up the attribute table to see what are the attributes that's there in this in this shapefile. So once you have this open, you will notice that there is a field called ACC_val, and the numbers in this variable refer to the ground acceleration or the seismic activity, seismic activity that's predicted for a large earthquake with a 2% chance occurring in every 50 years, expressed as a percentage of g, or the gravity, that is the acceleration of a body falling under the gravity. So this may be a little scientific information, but I just wanted to give you an information of what this ACC_val is. This stands for acceleration on the acceleration_ value, and this is sort of refers to the value of the ground acceleration predicted for the likelihood of a large earthquake. That's a likelihood of a large earthquake happening in that area with a 2% chance in every 50 years. This number, they go as high as 200, meaning that an earthquake with a ground acceleration of twice the value of the gravity. And the details of these units are not so very important to people. So, we will just classify or divide the value of ACC_val val as, from low seismic value to high seismic risk, for the high seismic risk of experiencing a damaging earthquake. So now that we have looked into the attributes of the seismic layer, we can close this, and we will go to this layer over here, and then we will switch to graduated. The column that we're going to select is ACC_val, which stands for acceleration_value. So the graduated classification allows the users of QGIS to break down the data in a column of unique set of classes, and these classes can be numeric classes such as from 1 to 5, 6 to 10, 11 to 15, like that, or it can also help, or the data can also be classified under the graduated category as from low to high values. So that's that with graduated symbology. And after we have selected the acceleration value over here, we'll just leave the method as color, just like that. Okay, and I will just hit on classify. So over here you see that okay, let me just like zoom into this layer over here. So over here you see that the seismic acceleration value is classified into the color range that goes from white to dark red. So the areas of white represent the areas with 0 or very, very less seismic activity, whereas the areas that are deep red in color represents areas that have very high seismic activity going in that area. So over here you can see that this area over here, which I represent, is the California area. This area represents high seismic activity, which is true because we know that San Francisco and California area, they have a lot of seismic activity going on in that area. And likewise, you see that this part of the United States does not really have much seismic activity going on, and it's likewise in other areas. So I'm just going to zoom out, and these values over here, note that it can also be altered, and to alter that you can give in values like 0 to 10. So in this case I will give out the values of 0 to 20 and 40 to 60, 60 to 80, and 80 to 100. Let us leave the last column as it is, and this figure over here, let's label it as low, and this one, let's label it as high. Okay. Sorry. You can also change the color ramp if you want. I mean, if you don't really want the low area of low seismic activity to be represented by the white color, you can select any other colors, but in my case I'm just leaving it the way it is. So now that we have mapped the area with high seismic activity, let's go and get the earthquake data. And I have the earthquake data over here, and what I'm going to do is I'm just going to drag and drop, so that will pull up the earthquake data for me. And if I just look at the attribute value, we have the time information, the latitude and longitude information, the magnitude of the earthquake, in this case it is 5.2 Richter scale, and the classification of the magnitude type. And yeah, so we also have the name of the place over here, 69 kilometers southwest of Old Iliamna, Alaska. And likewise we have many other information over here. So note that we have the magnitude information because this is the information that we are going to use to sort of use in the mapping of the earthquake data. Okay, just a quick correction. I think I got the I incorrectly dragged the earthquake file because this is a CSV file, and I wanted to map the latitude. I mean, I would like the QGIS to know that this file has latitude and longitude information. I should not have, just dragged and dropped the file. So I'm going to go over to the, I'm getting old, so sometimes I make a mess out of it, so bear with me. So I have it here. So latitude and longitude information, this is all correct. So I'm going to just edit and do close. Okay. So over here, what we have is the data points of all the earthquake incidents that happened in and around the world. So this is the historic data, the historic earthquake data. So we know that this part of the United States had a lot of earthquake going on, and there was also a bit of the earthquake that happened in this area. And we know that from this diagram there was a lot of earthquake that happened in the Mexico region. Okay, so this over here we have all the earthquake data over here. So the next thing that we're going to do is we are going to map these data points based on the magnitude of the earthquake, or based on the magnitude of the Richter scale. So higher the Richter scale of earthquake, the larger the circle, or the larger the data point is going to look. So that's what we're going to do next. And because I'm already running out of time for this one, I will see you in the other video.